We'll start by defining the plot that we're gonna use. That has to take neighbors, and then take the train scores, and then we'll label it by equal to train scores or score. We'll also do the same thing for the test scores, so you can see how each of these present. So in our case, we have the plot, same thing, take neighbors, this time we'll take the test scores, we'll label that by test score. Let's set the values in the x, plt dot x text is equal to range from, if you remember the array that we created, it was from 1 to 20. In case if it was more than that, then you have to implement the number that you've set it for. For example, in our case, it was 21, but in case you wanted to see, for example, 50 or 30, then you set this value to 30. In our case, 21, equal to 1 by 1. The increment goes by 1. And then we have also to put the x labels. Let's say that it's equal to the number of neighbors. Let's also put the y label. And that has to equal to the model score. So what actually we're gonna do is that we just gonna present each of these values, but in a more visual way, so it could be understood easily. So we've set also the y label. Let's also put some legend. We'll do print maximum KNN scores on the test data. Set the max to equal to the highest score that our testing data that has achieved, which I believe in our case it was 75. Test score. And let's multiply that with 100. So, it can show us as like a percentage. test score. That has to be scores. Let's take that R, and this has to be close test scores. Set the percentage sign. Now let's try to show it and see. Let's ensure that our libraries were called in case if you were disconnected. So let me ensure that our libraries are loaded again. Let's now run the code and see what would be the plot looks like. Okay, so as you could see that these were the training data scores. So it seems on the first in neighbors, when it's equal to 1, it has maybe the highest score of accuracy compared when the value were 20, which we have already observed here. So the line in blue represent the train scores, and the orange line represent the test scores. So if you've noticed, maybe when the number of neighbors were equal to 11 had the highest, when we have on 75%, our case it was, yeah, 75%, and that is equal when the neighbor is equal to n is equal to 11. So a key insight that we can learn from this graph is that this like plot, which allows you to observe the bias variance and the trade-offs. Even though that we have tried to tune the KNN model, however, the highest score achieved on the testing dataset, which is our main measure to measure the model accuracy, since it's being trained on scene data, but this time our testing data or our testing test set is crucial because it's been tested on unseen data, on a data that the model hasn't seen before. So I could see that there are some quite improvement compared to the baseline we have here. If you recall that our KNN model has achieved around maybe 68%, around 69%. So I think as of that, we have just done some, quite hyperparameter tuning for the number of neighbors. Think of the other hyperparameters that you can, improve or change in order to come up with a higher score than the 75% that we have achieved here. So as I mentioned, however, the highest score we achieved is 75%, which is still low compared to the goal that we have. If you recall that we have to have at least around 90% accuracy. So compared to the other models, like 75% isn't enough compared to the other models that we have. We have here around 83% for the random forest, and we have for the logistic regression around 86%. Still, after we have optimized the KNN model with defining the finding the neighbors parameters, we haven't seen, an accepted uh, score, which is around only 75%. It's still low, it's very low compared to the other models that we have. So, like a key takeoff here is, let's summarize it with saying that if the training score is much higher than the test score, especially for smaller n neighbors, the model may be overfitting. Like as you could see here, if there's a big variance between the training score and the testing score, the model may be overfitting. And also, let's say that as the n neighbor increases, as you could see, you should see that the test score is not that uh, fluctuated compared to the training score. As you could see, the training score has started with, let's say, around 80%, then dropped here when the n neighbors had equal to 5. Compared to the testing data set, it seems more to be more stabilized. And let's put like maybe there is some, there is no peaks, as we could see that. So this is a summary of how we can, fine tune the KNN model and represent the scores and upload that. It, could visualize the numbers that we have got. And this visualization helped us to identify the optimal number of neighbors, as we could see by finding where is the maybe the test accuracy is maximized. In our case, it was equal to 11. You can, also then return the model using the n neighbors value and evaluate the final performance on the test data set as what we have done. So think in case if we haven't any have, let's say, a testing data set and we are taking all of our decision based on the training data set, and then think on real world that when you include or when you add a new data set or you ask for to predict a new heart disease case where the model hasn't seen that data, we call it as real-time data or real-time or real-world data. Think of how the test score will look like. So that is the importance of having and testing your models based on the test data or the test scores, because it simulates the real world data as an unseen data.